Hello, this lecture will cover pages 117 through 122 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Combinational Logic Circuits, Part E, the BCD to Seven Segment Decoder Design. If you look on page number 117 of your lecture notes, the first thing I want to do before we get into this design on a BCD to 7-segment decoder is to talk about don't care conditions. If a particular input will never occur, or if it does occur and we know that it will not affect the operation of the overall system, then we may show this input on the K-map as a don't care symbol. Don't care symbols are shown with an X. X means that this particular input can be treated as a 1 or a 0 in the K-map. You only use don't cares as ones whenever it makes a larger group in the K-map. This leads to greater simplification of your design. Don't cares are like wildcards, but only use them when you need them. So let's look at a couple examples here. This first example, y is equal to sum of the midterms 2, 3, and 7, with don't care conditions be sum of the midterms 1 and 6. So if you take a look at our three variable map here, the midterms are 2, 3, and 7. We put a 1 in for 2, we put a 1 in for 3, we put in 1 in for 7. The don't cares are 1 and 6. We put an x in 1, we put an x in a 6 subcube. And we do not have to include all the x's. We only use x's if it will make a larger group. Well, if we include this x, we can get a group of 4 here. We have to make sure we get all the ones though. So this group of 4, if you take a look, y is equal to b. In your textbook on page 152 and 153, there's an example 415. If you have a different version, this is the example we're looking at here. It's going to be this example here that says, let's build a logic circuit that controls an elevator door in a 3-story building. So I want you to look that example over. Get your textbook out and look it over, and the design of that problem looks like this. You open the door when the sum of the midterms is 1, 2, and 4, and the don't care conditions are 3, 5, 6, 7, 11, 13, 14, and 15. So we put 1s in for a 1, 2, and a 4, a 1, a 2, and a 4, and we put x's in for all the don't care conditions. And you try to form the largest subcubes possible, and they have to be powers of 2, don't forget. A 1, a 4, a 1, a 2, a 4, an 8, a 16. So work this problem out, and these are the answers down here. Open is equal to this Boolean expression, and if we factor out an m bar, we get this for a final solution. That's a very good problem. Make sure you find it in the textbook and look it over. Great application. Okay, your homework assignment starts on page 119. It's just a part of your homework assignment. There's problems in the back of the textbook that you can see on page, let's see what page that is. It's on page number, I think it's on page 130. Let me take a look here. In your lecture notes, page 130, yeah, that's your homework assignment for the back of the book, but this is going to be due in 2 weeks. The specification is I want you to design a BCD to 7-segment decoder as shown below. You're going to design this circuit right here. You're going to have 4 inputs. This is your binary coded decimal, and when we do our truth table, instead of having an A, B, C, D across the top, let's do that a little different here. Let's call this the A3, A2, A1, and A0, with this being the most significant bit. So your truth table would start out with the inputs A3, A2, A1, and A0. What you're going to do is design the circuit that will drive this segment here. This is the rest of the specification. Let the above figure represent your block diagram. Use combinational logic design procedure given on page 100 to design the circuit. Your truth table requires 4 inputs and 7 outputs. So you're going to have 4 variable maps, and you're going to have to do 7 K-maps. The following 3 pages should help you in your design effort. So you could read the rest of this here. In particular, let's take a look down here. Down at the bottom it says each of the 4 BCD inputs should be generated using single pole, single throw switches with one side pulled up to VCC with a 1K resistor. The other side of the switch gets connected directly to digital ground. Remember, you cannot float digital inputs. And what do I mean by that? Each of these inputs here, I'm going to show you what you're going to have to do in multisim to put a 0 or 1 here, or 0 or 1 here, as you step through your possibilities to get a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 lit up here in this 7-segment LED display. If you get a single pull, single throw switch in multisim, what you're going to do is you're going to place that switch in right here, and you're going to get a normally closed switch. I'll explain that in a minute. Here's your switch. One side of the switch is going to go to ground, the other side of the switch is going to go to VCC, and you're going to pull it up through a 1K ohm resistor, and this is where you're going to take your input to your circuit. For instance, this could be A3, and you're going to do the same thing for A2, A1, and A0. So if you take a look, when this circuit, when this switch, this is a single pull, single throw, normally closed switch. You'll find that in your database. When it's closed, A3 is a 0. When this opens, A3 gets pulled up to 5 volts. So that's how you get your logic level 0 here, or your logic level 1 here with this switch, and you have to create this mini circuit 3 more times. If you take a look on page 120, you're going to go from your specification to your truth table, and I completed the truth table for you here. Notice your segments A, B, C, D, E, F, G. These are LED segments. Here's your block diagram. It's basically a 7447 chip you're designing. Don't worry about the order here. I wrote A3 first, being the most significant bit. And if you take a look, I'm defining how, if you put in a 0 on the input, you want it to drive segments A, B, C, D, E, and F. All these segments will be driven. The only one that won't be driven is G. G is going to be 0. If you want a 1, we want segments B and C to be lit up. Now, one might say, well, why not F and E? Well, the author decided that, and in most textbooks, most engineers, whenever you want to get a digital 1 in a 7-segment display, it's the B and the C segments that get lit. And a 2, and a 3, and a 4, and you go all the way down to 9. And you complete this. It's already completed for you. There's no 10, there's no 11, there's no 12, 13, 14, and 15, because there's no valid BCD codes for that. You'd have to go to 2 segments. You'd have to put another 7447 down here, and it would drive another 7-segment display. So these are all don't cares. From 10, 11, the whole way down. They're all don't care conditions. So if you take your time and you go through this, you're going to end up with 1, 2, 3, 4, 5, 6, 7 K-maps, 7 4-variable K-maps. I did a couple for you here. Map A, I think you have this on page 121, I've shown you, but here's the map for segment A. and here's the Boolean expression, and here's the implementation of it. Notice I'm trying to use NAND gates as much as possible. This is a 2-input NAND, a 2-input NAND, and a 4-input NAND. It's a 7420. So here's segment B. There's the K-map for segment B with the don't cares put in. Here's the Boolean expression. Here's the implementation of it. You're going to go ahead and you're going to do this 5 more times. And I think most students were able to do this with 20, I think 25, 24, 23 NAND gates. On page 122, I gave you an explanation here on this BCD to 7 segment output circuit. This is very important. Rather than reading it to you, make sure that you look over this page 122, and you like I said here, you read it until you understand it. We're going to be talking more about this in class over the next couple lectures, or in my video lectures, but I want you to notice here that the display that you're going to be using here in multisim, this is where you find it. It's under Indicators, Hex Display, 7 segment common anode. We're using the common anode, and we're going to drive these. LEDs with a low condition. This is a common anode here that's tied to all these LEDs. That's the CA here, and it goes to the VCC to forward bias these devices in here, these LEDs in here. And what we're going to do is drive the signal here high. We're going to put an inverter in all of our outputs because you'll be able to sink more current when you put these inverters in. If you don't have the inverter in, you're trying to source current out, and you just can't drive these these segments here. So what we're going to do is we're going to put an inverter in. All your outputs, when you're finished, you put an inverter in using a 2-input NAND gate tied together like I showed you. And then this will be a low active signal here. And that low active signal will forward bias the individual segments and turn them on. This explains all that up here. You want to read that. You probably need at least a couple weeks on that particular design. And if you have any questions, I can talk about it a little bit in the lab before we do some of our other lab work. It's a nice exercise. That concludes the lecture.